Today on Xenodon, I'll be tearing down a Formlabs Form 1 SLA 3D printer. Now, if you're looking for information on how to do 3D printing or use this particular device, this is not the video for you. So this got sent to me by a few individuals from a group that I'm part of called Photonsters, a bunch of really interesting and brilliant people. And they want to know exactly how to repair, upgrade, and improve the performance of this machine, and how to make their own DIY custom SLA printers. If you're into that kind of stuff, definitely would recommend joining the group. There are links below if you want to do that. My specialty is working with show lasers and other laser systems that use galvo-based beam steering systems, and this machine operates on a similar principle as one of those show lasers. In fact, for me, this is kind of a watered-down version because it uses pretty slow galvos and just a single 405 nanometer violet laser, which is what cures the UV active resin inside of the vat in one of these devices. So I'll be going over the mechanics of the device, the parts that are inside, such as the steppers, the galvos, and how the system controls those things, and how to make your own interfaces so you can make your own SLA printers, as well as in improving the overall performance of the Formlabs 3D printer, such as what galvos you can buy to make this thing operate faster, and maybe some minor tweaks that you can do on the laser. Anyway, let's get inside. The first thing I'm going to do is take off this orange acrylic top cover, and it's orange for a very good reason. The first reason is that it keeps unwanted ultraviolet light out of the working environment on the inside. Second thing is it protects your eyes from the violet laser that's on the inside. Has a very efficient means of blocking laser light, actually two of them. The first one is absorption. The second one is fluorescence conversion. So it takes that violet light and it converts it over into an orangey red light. It's very effective. It also helps keeps the environment inside stable during the printing process. Some people have put in little electric heaters that keep the inside warmer because I guess that improves print quality. We'll see just how effective this top cover is at blocking the laser light. And it's quite effective. It's like a 500 milliwatt laser pointer, and barely any gets through. This part looks to be a rather expensive part. One of the things I noticed is that it looks very handmade. Looks to be a cylinder that was maybe thermal formed from the four outside edges here, and you can tell that it's not the most even. About 3 millimeters of gap right here. Definitely has a handmade vibe to it. Probably one of the more expensive items on this entire machine just because of the labor involved to make this top cover. Put that down. Now we can access the upper portion of the actual base here. I think there's like 6 screws to undo. 2 right here in the back. And there's a couple more on each side. Alright, with those 6 screws done, this whole thing should lift straight up. And it does. Looks to be composed of mostly stamped and formed metal, probably cut out with either a water jet or plasma cutter, but nothing all too complicated. Most complicated part probably going to be that hinge. Alright, let's go ahead and remove the lower cover as well. This is going to need a lot of cleanup. There's a lot of resin inside of this unit. Yeah. Let's start with any screws that might be on the bottom. That's these all part of the frame. Yeah. So it looks like all of these hold on the inner assembly, and then we have the outside. So that's going to be Let's go ahead and remove the back panel. Yep, that's the back panel. Go ahead and clear that off. Let's see what else we can remove. It's all pretty much on one board. That's all mounted to the bottom, so let's go ahead and keep that where it is. Let's remove the front panel. Prime example of a mess. And 2 more screws on the bottom. Look at that. That's the front with the on switch. And there's a little OLED screen inside of here. Not too much going on. Pretty nicely formed. Now that we have access to the inside of the machine, let's go over how this whole device works. Let's start with this right here, and that's where your build plate clamps to. So your build plate clamps on the bottom right here. It's held in from the top. Now this is your Z-axis, and your first layer would start here and work your way down. So your positive Z numbers operate this way. It's driven up and down on this shaft right here. Shaft operates just like a screw, and there is a limiter switch here for letting the machine know when it reaches the top. It's driven by this little stepper motor right down here, which looks to be a 4038, so 40 millimeters by 40 millimeters by 38 millimeters deep. And there's nothing other than the bearings in the motor that is supporting the weight from this right here. It'd be nice to see some better load bearing type stuff on there. Let's go over here. Well, we got this little motor shaft right here. It's the same thing, drives 2 ways, and what that does is it controls the tilt of the resin vat. So, when you're doing your 3D printing, you'll have material, and that material gets secured on the bottom of the vat. Now, you have to raise the material up to add another layer. So what happens is the vat will actually rock. When it rocks, it'll break that printed layer off the surface of the bottom of your vat, lift it up, print another surface, break, print another surface, break, print another surface. So that's that little motor drive right here is what controls that tilt. On the inside of the machine, we have first surface mirror. That's going to need to be cleaned. And then we have the rest of the stuff on the back of the unit. So take a look at the galvos, control board, and power management for this whole system. In the back of the Form 1 3D printer, there's even more to take a look at. So this brings me to my specialty, and that's because this uses a laser and 2 beam steering galvanometers. So right here is the laser. That's a 100 milliwatt, 405 nanometer laser. And we have the galvanometers here. This is your Y galvanometer. This is your X galvanometer. And those are connected to a galvo amplifier. Now, this looks to be a digitally tuned galvo amplifier. So I'm betting that this chip right here is going to be a DSP, a digital signal processor. And then the analog front end. So it's going to be an analog amplifier. There are going to be analog input signals right here. The galvo outputs and 2 15 volt regulators. So going to be a positive and negative rail on that, which means that the galvanometer amplifier requires a split power. Probably in this case it's going to be positive 24 volts and negative 24 volts. Now that brings us to the main board. Now the main board only gets 24 volts in positive, so got to be getting that negative 24 volts from somewhere. Well, let's go ahead and explain that. So here's where the positive 24 volts comes in. There's a little poly fuse right here. And the first thing that really runs into is this MOSFET right here. Now I'm betting this is a P-channel MOSFET, and that's for reverse polarity protection. That sends energy this way, and the first thing we have is this DC to DC converter, which is controlled by this little chip right here. Now, I'm assuming that this gives us our negative 24 volt rail, and we can easily confirm that using the multimeter. And it doesn't look to be a synchronous buck because there's one MOSFET, which is this component right here, and one diode. So the output of the diode is going to be what provides us that voltage. Because it's a negative voltage, the power is going to come in through the cathode of that diode and go out this way. So if it is our negative voltage rail for the galvanometer amp, we're going to have zero continuity between, dead short, basically continuity between the output of that diode and the negative side of the galvanometer power supply. Now let's see if that's what we get. So to test that, we're going to take a look at this block right here, and it should be galvo rail negative, so negative 24, ground, and positive 24. Now I'm going to test between here and our negative side here, and if we see 0 ohms, that'll be what we get. So on the anode side of the diode, and right here, you can't see the meter yet. Now you can. Alright, so testing. Yep. So that's where we're getting our negative 24 volt rail from to drive the galvanometer amplifier. From there we have another DC to DC section right here. It looks like it's 2 different voltages. So we have a positive and a negative side, or the 5 volt. We're driving the op amps. That'll give us our analog differential going to the galvanometer amps, but it could also be powering different parts on here. So let's go over what we have. We have the drive chip for that, which drives the DC to DC section here. And over here is where all of the smart bits are, for the most part. So we have an ARM microprocessor right here. This right here in the back is what powers the 2 stepper motors. So it powers the Z-axis stepper motor, which is this one, I think, right here. Yep. And then we have another stepper motor output that goes to the one that does the tilting of the vat. We have our laser output right here. So I think this is an LM393. That's an operational amplifier. We'll have another little component right there somewhere, which should be a stable voltage reference, and I'm betting that this goes right out to the laser output. So it could be just a N-channel or an NPN transistor. USB output, a couple of other plugs. Yeah, lots of stuff going on. So what I want to do is I want to test the voltages going to the galvo as far as the signal, a couple of other things, really figure out how this thing operates. So first thing to do, hook up some power to it and do some probing. The most important thing to go over in this video is how the 2 laser beam steering galvanometers over here operate. You have one for X and one for Y. They get their power from these 3 wires right here. The yellow is the negative 24 volts. We have a black common, and we have a positive 24 volts on the red. So 48 volts between the yellow and the red. Yeah, it looks like there are 2 parts here for power. So my suspicion is that they were intending to use 2 analog galvanometer amplifiers instead of this fancy DSP amplifier right here. And I think they used the PT20s. We have 2 signal outputs right here. So here's your Y signal and your X signal coming from the main board. We have 3 wires on each one of them. So the black on the right side is the ground. So these 2 blacks are tied together. Then we have our differential signaling. So they work kind of like how you'd feed a signal into an operational amplifier. So an A signal and a B signal. And what these are doing is they're sending out a differential one way or the other. So the galvo amplifier is looking for 2 things. It's looking for the polarity between those 2 pins, and it's looking for the voltage differential between those 2 pins. So how these get their signal is they derive it from these 2 components right here. We have this little component, which is, I think, an OPA 366 operational amplifier, and this 2-channel DAC made by Analog Devices. Now, I can't find the exact part number, and that's because I think all of the information is on the back of the IC. Let's go over how this is all connected. So, as I said, these 2 grounds right here are going to be connected together. just like that. The two negative sides of the differential are also connected. No, just like that. And they are getting their signal through a couple of 0 ohm resistors and from the output of the operational amplifier, like so. Connect. There we go, I got it. And then the two positive sides of the differential are getting their output signal from pin 1 and pin 2. So the X positive side of the differential is pin 1. And we move over to the positive differential side of the Y and go over to pin 2. So those two parts are very important, and I might pull this IC off, but I think any dual channel DAC will work just fine. Let's go over how the differential signaling works. I'm going to start up the 3D printer. Now the one thing that I found interesting is that if I measure against ground and I go to the differential pins, I get a positive voltage on each. So positive 2.5. Positive 2.5. But that's not important because between the two pins of the differential, we get nada. So should work with any galvo kit that works with differential signaling. And we're going to try this on one of my own galvo kits later on. I want to pull this signal pin off. You'll notice that this galvo will twitch a little bit. Or not. This is really quick. And now I'm going to put my meter into diode check. What diode check does is it provides me a voltage between the two probes. And I'll be able to use that to check the differential signaling. So we'll put a positive on there, which is the red wire, and we'll put the negative on the white wire. You'll see that the galvo operates in the counterclockwise. And if I reverse those, we'll get the exact same deflection in the clockwise. So I'm betting we're going to see a 5-volt differential signal going to each one of the galvos, which I suspect is just fine. So yeah, I'm going to test this out in my own galvo kit. Should be fun. At this point, I want to see what the differential voltage is going to the galvos as far as the signal. So what I have here is just a simple model in preform. And it's a 10 millimeter tall by 125 millimeter by 125 millimeter wall. And this will give me the maximum travel on both the X and the Y galvos. So that way I can see the maximum signal voltage that's going into those. What I'm going to do to check the signal voltage is I'm going to use this capacitor and diode. And what this will do is when the galvos get a signal from that pin header, it'll charge it up one way. So it'll give me the maximum voltage differential going in one direction. And then what I'll do is I'll bend the pins the other way and measure the voltage going the other way. But this shouldn't mess with any of the signals going to the galvos. And it'll go across the positive minus voltage differential input pins. I won't be doing any measurement on the ground pin at all. So let's start this up. First thing I'm going to do is I'm going to set this in with the negative side of the capacitor on the negative side of the differential. And I expect to see this charge up to about 5 volts if I'm correct. And it'll be 5 volts, about the same going the other way too. And hopefully we won't get a capacitor going bang because the diode should be doing its job. Let's plug this in. Alright, I've never connected this up to this particular laptop before or tried to print anything. So there's a magnet that needs to be placed on this little safety interlock here. This is a cover close detection, and that magnet will make the printer think that the cover's all good to go. And it's not. It's ready to print. I've got a piece of plastic over the area where the vat goes. This will be the first time seeing the laser power up as well. This all goes according to plan. Alright. Print. Job name, frame. Send to printer. Right. So you select printer. No Form 1 printer is detected. But it's plugged in. But you're plugged in. Alright, all of our technical difficulties have been hopefully sorted out. Let's try this. It's singing. Okay, the Z is going down. Come on, laser. No laser or galvo movement yet. Ah, there it goes. Oh, that's quite nice. Alright, cool. Well, let's get a voltage on that. See if it's 5 volts. I'm betting it is. Go show that I'm wrong. $1.8. That's lower than expected. Let's see if it's the same thing. 1.8 on the other side. Oh, that didn't make it happy. It's just thinking. Alright. Crisis averted. Just printer work. Alright, let's see what the voltage is this way. A little more. Okay, so yeah, it's about the differential. It's about 2 volts. Much lower than expected. Interesting. That does look pretty cool. Definitely do see the laser beam doing its thing. Let's take a look at that. And there's our wall. Okay, it looks like a differential of about 2 volts. Differential signal. That's lower than what I see in show lasers, but that should work just fine with the other galvanometers. And those are sitting right over there. I'm going to hook those up, see if we can get those to make the same square as we're getting on the top there. So that's the next step. Now it's time to see if this will drive regular off-the-shelf analog galvanometers. So I've got the 2 analog galvanometer amps here. They're connected up to a separate 24-volt power supply over here. The galvos are actually right there. See the black? And I have a little beam. So what I'm going to try to do is I'm going to make a square on that black plate if this all goes well. If it doesn't go well, some smoke may escape. But that's why I do these things. For the excitement. It's like gambling with fireworks. Okay, so the first thing we're going to do is plug in my galvo kit, and that should home in. So go back up here, plug it in. Alright, that moved. I gotta center that real quick. Alright, so that should be galvo center. So now I'm going to unplug the galvos that are here, signals. Oh, don't need that. Don't need that. It is ready to print, by the way, so once this is all connected up and no smoke is being released, we can press a button and test. Alright, so I'm going to plug this in. Same orientation as the original galvos. So hopefully that dot won't move. That's not what we want. Perfect. Alright, plug in the other galvo. Same orientation. Hey, so far no smoke. That's excellent. Alright, so that's all connected. Running 2 different galvo amplifiers. I'm not running the internal galvos at all, and this is getting absolutely no signal, so we're not expecting any movement here, other than a couple of laser flashes. We're expecting movement on my galvos instead right from the printer. So the dot is still centered. And technically all I need to do is hit print and we should see square start to be made. Alright, here we go. And there's our squares. So, yeah. Since the galvos for my show laser tend to use a higher signal, it tends to make bigger scan angles with 5 volts instead of a differential of 2 volts. So it's a quite tiny square. But yeah, you can absolutely use off-the-shelf analog galvanometers in the Form and Form 1 Plus. That's perfect. That's exactly what I wanted to see. At this point, I'm going to clean up the Formlabs 3D printer a bit more, so I think I'm going to pull off the bottom and throw that in some soapy water because it's quite sticky in there. But before I do that, I want to go over some design considerations of which you might want to think on if you're building your own 3D printer that uses galvanometers like this. So one of the main design considerations is the reason they use this mirror right here. Now, why would you use a mirror and not have the galvos directly here pointing up? Well, the mirror plays an important role, and its main function is to increase the distance from the output of the galvanometers and laser to where the vat rests. Now, why would you want to increase distance? Well, there are 2 main factors to consider. So let's take a look at the first factor. Here I have the X and the Y galvo, and we can think about this as the bottom of our vat. Now, if the vat is close to the galvanometers, they're going to have to rotate more in order to accomplish the same amount of travel on the X and Y coordinates. Whereas if the galvos are further away, they don't have to rotate so much to cover the same distance. So therefore, your galvos aren't stressed out as much, they'll run longer, and they'll be quicker because you don't have to wait for them to move as far. So that's one upside. The second upside is the laser focusing. So if you have the laser close to the vat, the problem is that your focal distance is not only closer, but it's also shorter. That area where you get the maximum tightness in your beam profile. To demonstrate this, I'll show you a little 405 nanometer laser that uses a 4mm lens, and I have this focused at a pretty short distance. So I'm going to shine this laser here, and we'll be looking at something like this. So it's about 3 inches away. That's my tightest focal point. But if I move up and down, you'll see that the size of the beam changes pretty quickly. So that's what we're looking at. But if we have a longer laser beam, we can also elongate the thinnest portion of where that beam overlaps, making it thinner. Now there are a couple of ways to accomplish the best beam profile, but this is one that you might want to consider. So here I have a blue laser module, and on the inside, instead of using a 4mm lens, it actually uses a little 2mm lens. And the lens was pulled from a Show WX Pico projector. So you can see inside there, very small lens in contrast to the other one. The other thing I'm going to demonstrate is what this looks like as far as consistency further away. So instead of about a 3-inch distance, I'm going to be about a foot away from this area here. So let's see what the beam profile looks like when tilting it. There you go, that's about a foot away. And you can see that the beam profile stays much more consistent. And that's because you have much more area in the tight focal portion of your beam to play around with. So if the beam were center, you'd be starting right at the bottom. And as you go further out on the X and Y, you'd be going more and more into the thinnest area of your beam. But yeah, much more to play with. So those are two considerations that you definitely want to think about when designing your own 3D printer. Now that I have the bare inner mechanical assembly, let's take a look at how that's put together and go over some more design considerations that will help you build your own basic DIY galvanometer based SLA printer. Now this inner assembly looks pretty complicated, but we can break it down into two boxes that have simple functions. This right here and this back section here. Now the front box has two main functions. The first function is that one side must tilt down, so that way it can perform its break and peel operation between layers. So if you notice here, the side is taller, the side is shorter. There's a hinge right here, and this side is driven by the stepper motor, so that way it can lower down. There is a fixed lead screw right here that's attached to this little hinge, and that hinge is there so the angle between the lead screw and the vat can change as it's lowered and raised. That's important. Now the way this stepper motor works is on the inside there's a nut that spins, and the lead screw is mechanically fixed so it doesn't rotate at all. This whole assembly will raise and lower, and thus this as well. Now you can use a rotating lead screw. If you do, you have the stepper down here. You can have a lead screw nut here that doesn't rotate, and as the lead screw rotates, it would control the height of the vat. However, you'll have to have a hole in the top so the lead screw can go through the top as it's being lowered, or find a way to counteract that offset of the lead screw. You'll also have to have a mechanical linkage to compensate for the change of angle. As it goes down, the angle will get smaller. As it goes up, the angle will get bigger. So you can have the lead screw nut fixed from both sides, so that way it can rotate back and forth. Having the motor up here would be a little bit more complicated because once again you have to deal with that mechanical linkage. The second design function is that it has the 45-degree mirror mount inside, and that reflects the image that's being drawn by the galvanometers and laser up at 90 degrees and onto the bottom of your build plate. Now the second box is this box back here, and it has a couple of things inside. It has a linear slide bearing, linear slide rail, and that gives us a mechanical stiffness and allows this piece to travel back and forth and maintain rigidity. And these come in different lengths and widths that you can find for your own SLA printer. That mechanical movement is driven by this lead screw right here. Talked about this earlier. When it rotates one way, this part right here will lower and raise. and it's because the lead screw nut is inside here. So it's like if you're turning a screw, it'll raise and lower the position of the nut because that is mechanically fixed and can't rotate. The stepper motor that it's driven by, you can find these almost anywhere. They're pretty common. If you're using one as a replacement in your 3D printer that you already have, you'll have to note how many steps there are in a full rotation. If you're designing your own 3D printer, you can play around with the amount of steps per rotation. The more steps per rotation that you have, the more detail you'll have as far as resolution. So, two basic pieces that are fixed together. If you get two metal boxes that are pretty well constructed, that would be a great starting point for your own 3D printer frame. Let's talk about the laser beam steering galvos a bit more. So here's the original galvo block from a Formlabs printer, and it's basically just a mechanical mount that holds the two galvos in. This one is clamped in with this screw here, and this one is clamped in with this screw here. It also holds the laser on this side and has a 45-degree angled mirror here, so it reflects the laser light from the galvos up 90 degrees and out. Now, these are fairly common galvos to find. As I said before in the video, I think these are the PT20s, which are 20 kpps galvos. A couple of things to note. You can find replacement galvos pretty easily. I'll leave some links down below in the description so you can purchase replacements. Some galvos are a bit smaller, some galvos are a bit bigger in diameter in this section here. If your galvo is too small, you can use a section of tubing with a slit cut in the side, and that makes a great shim. If your galvo is a little bit bigger and won't fit, you can always drill this out with a larger drill bit that matches the diameter of your new galvo. But a lot of galvos are going to be the same diameter. You can always reference the data sheet as well, but there's nothing fancy about these. Well, the only thing neat is this one is a dielectric mirror. You can see that it has blue reflection. That's tuned for the 405 nanometer laser light, blue light. Well, it's off center, isn't it? Oh, my OCD. Stop looking at it. Alright, so if you can't use this block with your galvos and you have a separate galvo block that came with your galvo kit, like this block, you can mount it in like this. So you have access to both of the clamps to clamp your galvos in. You're also going to need to find your own mirror or use the original and build your own mount. So you'd have to mount that mirror at a 45-degree angle just like they did in their mount. Let's talk about the amplifiers. So here's the original one from the Formlabs, and I thought they were using a microprocessor to tune the galvo, which they are, and for doing digital protocols like the XY2-100, but that's not the case. It's actually something pretty clever. So they're using an ST32 micro, a microprocessor, same one I think they use in the Arduinos. But what it's doing is it's tuning these chips, and these chips are 8-bit digital potentiometers. That's all they are, just digital potentiometers. They have a little voltage divider network inside, and you can tune them basically in different points of resolution depending on the resolution of the serial input. As I said, these are 8-bit. Yeah, interesting. So pins 11, 10, and 9 are the potentiometer legs. So if one of these chips fail, you could just replace it with a potentiometer in most cases, I'm betting. But why they did this is it allows them to make these galvo amplifier boards really quickly because they can just plug in a dongle and then just tune the microchip. So they can make a lot of these really easily. Now, a little bit of a rant. I don't like this because there's very little advantage to doing this for the end user. When you get an analog amplifier that doesn't have a microprocessor on it, you can always tune it. Earlier in the video, I said a lot of show lasers use a differential signal that's 5 volts, so you'll have to change the size on your analog galvo amp in some cases, and that's usually the potentiometer that doesn't have any glue on the top, preventing it to be tuned. Get yourself a turnpot tool and adjust the size, and you'll be fine. Most galvo amplifiers that are analog will work with the Formlabs 1 and 1 Plus. So we looked at this one earlier that uses the ground pin and the plus and minus differential pins, but most analog amplifiers use the same thing. So on this one it's a little different. You got two ground pins here, and you got the positive and got the negative. So you can see the grounds are tied on the bottom right there. Same thing with this galvanometer amplifier by Gold Star. And we take a look at the input pins. So same thing, ground, positive, minus for the differential. This will work just fine. Same thing with this one here. We got the ground, negative and positive for the differential. Yeah, all of these analog amplifiers are suitable replacements. And that means that you can repair your Formlabs 1 and 1 Plus 3D printer almost indefinitely, which is great. Alright, let's go over the main board in a bit more detail. I'll try to be quick and concise as I am racing the dying camera battery, and there's lots of information to tell you. So let's do it. Alright, let's talk about the area that does the serial data conversion to the analog voltage that we need for the differential to drive the signal going to the galvanometers. So that's these two parts right here. This is the OPA 336 operational amplifier, and I took this IC off to look for a product identifier number on the bottom. Sure enough, there it was. So there were two rows, 404, and the lower row that's 5543, which tells me it's a 12-bit dual channel DAC. Its output voltage, I believe, is 0 to 5 volts, which makes perfect sense in the way that they're using this chip. Let's go over the diagram. Now, the datasheet that I found for the AD5443 did show the same pin count and the same package. However, there were some differences in the pin assignment. Now let's go over the circuit they have in the Formlabs. I got 5 volts that comes into here, goes to these two pins, and then goes to power the operational amplifier, V plus input. Then we have the ground rail, which is right here, 0 volts. Powers the operational amplifier, goes to ground on the DAC. You have the two output pins right here, out 1 and out 2. And what they do is they put out a voltage anywhere from 0 to 5 volts, depending on the serial data that you feed them. So how does this whole circuit work? Well, what's going on is one of the pins on the DAC seems to be controlling the output of the operational amplifier, so we get an output voltage that's 2.5 volts. So the negative side of the differential, which I drew in green, is always at positive 2.5 volts. So what happens is if we want the galvo to go up in coordinates, we start here on the output at 2.5 volts, and we give this a higher voltage than 2.5 volts up to 5 volts, which will drive this side of the differential positive. Now, if we start at 2.5 volts and go towards ground, now we have a lower voltage on the output pin than we do on the 2.5 volts that's coming from the operational amplifier. So the positive pin sees a negative signal, negative bias, compared to the negative pin of the differential input. So our 0 position is 2.5 volts. Anything above 2.5 volts on the output is our positive coordinates. Anything lower than 2.5 volts is going to be our negative coordinates. Now keep in mind, when I was taking a look at the differential voltage and I was using the capacitor with a diode, we get a voltage drop on the diode of about 0.6 volts, which, adding that to the 1.9 we saw, gives us our 2.5 volts. That is our 0 position. So that's how they're using the DAC. Now, as I said, there were some pins that were a little different. Let's take a look at that. So we have serial data in, and we have our clock, and those are tied to the positive side of the input coming from one capacitor I'll point out later on in the video. That's kind of weird. Now the other weird thing is that the area or the pin that we should be getting our positive 5 volts to power the chip is actually getting a signal from the microcontroller on the board, which is also odd. Let's see, we have sync, which is connected to the microcontroller, and we have the serial data out, which is also connected to the microcontroller. Now, I have no idea why they would even need the serial data out going to the microcontroller. There's no reason for that at all.
I could easily see the resistive feedback being capable of driving the operational amplifier, and I could definitely see positive being tied to the voltage reference of the DAC as it is in the diagram. But if you want to control galvos, this is a very simple way to do it. As I said, you can use nearly any DAC. If it's a 2-channel DAC, you can find DACs on sound cards. Sometimes the voltage isn't high enough and you need to boost the output with operational amplifiers. I'll link below in the description a DIY galvo page. It'll help you build your own circuits for that. Or if you want to use a circuit like this, that's also an option. The only downside to this circuit is that you won't get the full plus minus 5 volt differential from ground. You'll be stuck with only a 2.5 volt differential voltage to drive the signal going to your galvos. Now that I've gone over the section of the main board over here that handles the analog signals going out to the galvanometers, let's talk about the other areas. So earlier in the video, I talked about this area here, which is the DC to DC converter section that takes positive 24 volts and turns it into a negative 24 volt rail for the galvanometer amplifiers. This right here is another DC to DC section here, and it gives us a few 5 volt rails. One of those rails goes out to the DAC and the operational amplifier. The other voltage rails goes to portions on the main board over here. So they power the microprocessor and the laser. Let's take a look at the microprocessor, which is an ARM Cortex M3. So if you're looking for a microprocessor for your own DIY printer, I'd say look at the ARM Cortex series. This one being the STM32F103. This is a 72 megahertz 32-bit processor. Over here we have the section that controls the output of the laser. And we have an LM358, and we have an NPN channel, an NPN transistor. There are two things that connect to the laser output. One of them is a photodiode, the other one is a laser diode. It looks like the photodiode is for feedback, which controls the current going to the laser diode. It doesn't look like that the photodiode is connected to the microprocessor at all, so I don't think the microprocessor actually has any active feedback as far as what's going to the laser. So, yeah. I think right here is the voltage divider network for setting the output going from the op amp, which controls the current going to the laser diode. And I think this resistor right here is connected to pin 20 on the microcontroller. So I want to attach my own laser module to that. What I'll be doing is I'll be tying the positive modulation pin to this side of the resistor and the negative side of the modulation probably to this ground right here. Let's see if that works. Let's take a look at this chip right here. It's a dual stepper driver. Now, if you need to control your own stepper motors with a microcontroller, you can get these, and these are single stepper motor driver modules. They work well with Arduino and other microcontrollers. They have all the pin assignments on the bottom, and they work pretty well. The stepper driver itself gets its power directly from the positive 24 volt rail. Let's see what else we have here. Ah yes, that chip. It's actually a chip that contains its own thermistor, and what this chip does is it's a thermometer, and it tells the microcontroller what temperature the inside of the printer is at. And this can help with regulating the power of the laser. How I think this works is that the chip uses PWM, so if your printer is warmer, it'll fire the laser less because the materials are already warm and they can solidify easier. And if it's cooler, it'll pick that up and it'll give the laser pulse a higher duty cycle to compensate for the resin being colder and therefore not as easy to transition into a solid polymer. Yeah, that's about it for this board. And now for the last test that I want to do before I get this whole printer put back together, and that's to try to modulate this laser using the signal on pin 20. coming off the microprocessor. So this laser takes a modulation signal. It's 5 volts, and I should be getting a 5 volt modulation signal from the microcontroller. And I have this pin right here, which is the ground pin on the calibration pin header. So what I'm going to do now is I'm going to attach this driver to positive 12 volts to the power supply. Attach that here. And I'm going to turn on that power supply. Alright, that's good. The last thing to do is connect the modulation wire up and see what we get. So here's the modulation wire that I have. That'll connect to my modulation input on this laser. Hey, no laser light. That's a good sign. So both lasers should operate at the same time. I already have this set up to print. Let's go ahead and hit the print button, see what we get. Is pin 20 our magic pin? Get down! Alright, anytime now. Well, that laser's working, but this one isn't. Oh. Maybe the voltage isn't high enough. Let's go see what we're getting for a modulation voltage. This is an analog laser driver, so the voltage isn't high enough. We might not see any output. That should be working. Interesting. Go ahead and do some probing. Voltage. What do we get? Can we hear ground? Ah, 1.6 volts. Okay, well, an analog laser driver is not going to work. I need to go and find one of my TTL ones. Alright, I have a laser now that takes a TTL signal instead of an analog signal. The only difference is a TTL is straight on and off and works well with PWM. And an analog laser works well with a voltage that can scale from 0 to 5 volts. So one of them is on and off, the other one is linear. And we weren't getting enough signal power to drive an analog laser driver. So it looks like it definitely does use PWM. There's no scaling of the laser power output at all from the microcontroller. Let's go ahead and see if it works with a TTL laser and if we have luck with pin 20 on the microcontroller. So let's start it off. Yes. Here we go. Alright, let's see if this laser right here does the same thing as the violet laser on the inside of the machine. Hopefully it does, because it'd be nice to know that you can use your own laser instead of having to deal with all the laser bits they have on the inside. And this will tell us. Alright, fingers crossed. Oh, it's on. Oh, excellent, 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 excellent. Is it doing the same thing? Let's see. Yes, you can use your own laser driver and laser in the Formlabs off pin 20, it looks like. That's working perfect. Yeah. Okay. Yep, I've just verified that pin 20 on the microcontroller is for laser control. And it does operate on PWM, so if you choose to use your own laser, you'll need to have a driver that uses TTL, as a transistor logic. But yeah, absolutely. Put whatever laser you want in here. You don't have to worry about their own integrated laser driver. None of that. Just use pin 20 and a ground reference for your signal going to your selected laser module, and you'll be fine. How you fit it in the mount, well, that's a whole different story. But you're smart. You watch my channel, you'll figure it out. Let's put this printer back together and wrap up the video.
And now to wrap up the video with some thoughts on the Form 1 Plus. Let's go over the pros and cons. The pros. This printer is easy to use and highly serviceable. There is nothing in the Form 1 Plus that is in a closed hardware ecosystem, which means that you can get replacement stepper motors and galvanometers easily. You can also do your own laser modifications and installation. About the only thing you can't easily repair is the firmware and programming. The cons. The Form 1 Plus is a slow printer, and this comes down to a few things. The first is that the laser power is quite low. With a more powerful laser, this printer could operate much faster. The galvos themselves are also pretty slow, but this is compared to the show laser standard of 30 kpps. Despite the galvo speed, I know that the stock ones can mechanically perform quicker than they currently operate in this printer. The other drawback to this printer is that the laser does not maintain a constant angle while scanning on the bottom of the fab. So instead of scanning like this, it scans like this. To further help you, there will be some links below. These links include places to purchase various galvanometers and galvo amps, do-it-yourself digital to analog circuits that you can build that will allow you to control galvanometers using a microcontroller, and a teardown of the original Formlabs Form 1 Plus laser. If you're considering building your own laser for the Formlabs printer, another thing to consider is purchasing a laser that is much more powerful, such as one using the BDR-209, and then using a spatial mode filter, which is basically just a small hole that blocks the waste beam. It's quite common in high accuracy laser systems to sacrifice power for quality. This may be an easier route, as finding a small lens for collimating the beam might be more difficult. I also want to do a video on rebuilding the original Formlabs Form 1 Plus laser, so if you have a broken one, consider sending it my way. Now, even though the microcontroller seems to use PWM to run the laser, there is still a chance that it's analog modulation, as the laser circuit itself can be operated linearly, just with a lower modulation signal voltage. If I find that's the case, I will see about amplifying the signal to operate it with a 0 to 5 volt analog signal. At this point, there is very limited testing and modifying I can do, because I do not have a build plate or VAT. A follow-up video will eventually be posted, but since I work with mostly metal and glass, it's not a priority to get the Form 1 Plus printing anytime soon. In the future, I want to get this printer running much faster, which would include a stronger laser system, possibly faster galvanometers, and custom firmware. Since I do not do programming, this would have to be a collaboration with someone who can. Hopefully that'll happen and be in a future video. Another thing I want to do is eventually design a small digital to analog PCB module that can easily be used with various microcontroller units for do-it-yourself galvanometer based projects. The last thing really that comes to mind is that I want to obtain a pair of the newer Formlabs galvanometers and compare their performance to high-end galvos and show lasers, as I think that would be a quite fun project to do. That's about it for this video. I hope this helps you work on your own Form 1 Plus, and as always, stay tuned for more.